Alright, this is our second problem, and this problem is taken from the textbook by Philpott, Mechanics of Materials. This is example 1.2. It says here a rigid bar ABC is supported by a pin at A and actual member 1, which has a cross-sectional area of 540 mm squared. The weight of rigid bar can be neglected. Okay, so here is our system, and this is the rigid bar. And this is our actual member right here. That's the actual member 1. Okay, and recall that when you say rigid bar, it doesn't deform. So it can just translate or it can rotate, but it doesn't deform. Okay, so here this rigid bar is connected at A and also at B, being supported by this actual member, and we have this force, applied force P or external force F. Okay, and sometimes it's just symbols that they use that they use P for external force or F, so that doesn't matter. We just have to understand that when we talk about stresses, we are referring to internal forces. Okay, so the distance from A to B is 1.6 meters, and the distance from A to C is 2.2 meters. Now, if for letter A, determine the normal stress in member 1 if a load P is equal to 8 kilonewtons is applied at C. So if I apply a load of 8 kilonewtons, then what's gonna be the normal stress right here? And for B, if the maximum normal stress is in member 1 must be limited to 50 megapascals, what is the maximum load magnitude P that may be applied to the rigid bar at C? Okay, so let's solve for A first. Okay, so drawing the free body diagram and solve for support reactions and forces and force at actual member. Okay, so here is our so this is our P, and this is 8 kilonewtons, and this is a pin, so we have two support reactions. All right, now in terms of the distance, we have 1.6. Okay, this is 1.6, and then this is 2.2 meters. Okay, so now let's apply the equations of equilibrium. The summation of moments, let's take summation of moments at A is equal to 0. And if you take this, what you get is a By is equal to 11 kN. Okay, so we're not going through the details of the computation here because we have done a lot already. So whenever we get into the equilibrium equations, we'll just do shortcuts. Okay, and if you do by the way, this By, this is it. This is the By, right? Let's just write it here, By. Okay, so this is our By. So the By is 11 kN. Okay, so now since we have the force, and this force is actually it's just this external force is just equal to the internal force anywhere along this actual member. So since we have the force and the area is given, therefore we can solve for stress. So sigma is equal to b sub y all over a. Okay, so this is 11,000. This is 11,000 Newton divided by the area of 540. Right, 540 mm squared. Okay, so what we get is 20.37, and recall that this Newton per mm squared, this is just equal to megapascals. Okay, we have the stress, and that's our answer for letter A. Now for letter B. Okay, so for letter B, so let's draw the FBD for letter B. Okay. So it says here that if the maximum normal stress in member must be applied to 150 megapascals. So if we have this By, and here is what's gonna be the maximum load P here. Okay, so right here we have the support reactions. Let's say this is AX, this is AY, AX and AY. Okay, so the second question is that this one is given, the By, and we are to find this P. Okay, so this By can be obtained using the stress equation because we have the stress, allowable stress of 50 megapascals, and we have the area, then therefore we can solve for the By. Okay, so for the By, solving for By. Okay, so P is just equal to By, or no, we just rather write By is equal to theta, the stress times the area. Okay, so the stress is 50 megapascals, right, times the area of 540 mm squared, and this is 27,000 Newton. Okay, so once we have this 27,000 Newton, then we substitute that here to the By, and then we can obtain for the P. Okay, so let's write it here. Substituting By and take moment at A. Okay, so summation of moments at A is equal to 0. Alright, let's just start in the new sheet. Summation of moments at A is equal to 0. Alright, so we have By. Okay, so By times the distance, 1.6. And right here, the distance is 2.2 meters. Okay, so By times 1.6 is equal to P. Right, P or F, right here, this P is times the moment arm of 2.2. Okay, so P therefore is 19.64 kilonewtons. Okay, so just to have a recap on what we did. So the first problem is to solve for the stress in this bar given the external force, and the second problem is given the stress, what is the external force right here. Okay, so we just apply the equilibrium equations, and since we have the given area, then we can solve for the stress. Okay, and for the second problem, since we have the stress, then we do it backward. Okay, so we apply the stress equation and we obtain the By. Once we have the by, then we can apply the equilibrium equations to solve for this external force P. Okay, so that's all. Okay, so the next sample problem is taken from the textbook by Beer and Johnston and Daywolf, and this is example 2.01. And it's found in page 62. Okay, so the problem says determine the deformation of the steel rod shown in the figure under the given loads. So we have this E is equal to 29 times 10 to the 6 psi. Okay, so here is our actual member, and it is subjected to multiple points loading, and also the cross-sectional area is different. Okay, so here's one point, and this is 75 kips, and another point is 45 kips, but this is to the left, and here we have 30 kips, and that's to the right. So the distance from A to B, this is 12 inches, from B to C is 12 inches, and from C to D is 16 inches. Now right here, the cross-sectional area is 0.9 inches squared, and right here, this section, this is 0.3 inches squared. Okay, so how do we solve for the deflection is to use these equations, right? So since we have a multiple point loadings, and we also have a non-uniform cross sections, I mean a composite cross sections, then we should apply these equations. Okay, so it's the deflection in this section plus the deflection in this section. Okay, so first step is to draw FBD and make cut sections. Okay. Okay, so first section is right here, because this section will represent any any sections from this point to that point. By the way, let's also include the loadings. We have 45, and right here we have 30, and right here we have 75 kips. Okay, so we need to make a section cut right here, because that's gonna be the representation for all, the representation in all these sections, or in all the segment. Okay, so right here, let's draw. Okay, so let's expose the loads, right? So we have 30. So if we have 30 right here, since we had a section cut, then this is going to be the internal force, right? So let's just label this P3. Okay, then we need to make another cut right here. Okay, so if we have 30, and right here we have 45, and since this is a section cut, then let's just assume that this is the direction. So if we obtain a negative value, then it just means that it's going the other way around. Okay, so let's just denote this as P sub 2. Okay, and then another section cut that will represent from point A to point B. this is 30, this is 45, and this is 75. So because this is a section cut, then there's also a internal force right here. Okay, so meaning this is section 1, right? This is section 2, and then this is section 3. Okay, so the next step is calculating the internal forces at cut sections 1, 2, and 3. Okay, by using the equilibrium equation. Okay, so refer to figure 1. Let's say this is figure 1. Figure number 1. So let's write it here. Refer to figure 1. Okay, so let's start with this P1. Okay, so P1. Okay, so let's say we have a this direction. I mean, all directions to the left. Let's say that's negative, and all directions going to the right, that's positive. Okay, so this is negative P sub 1. Okay, so plus, okay, this is negative P sub 1 plus 75 minus 45 plus 30. Plus 75 minus 45 plus 30 is equal to 0. Okay, so we only have one unknowns, so P1 is equal to 60 kips, and this is in tension. So positive, meaning we have a tension force right here. Okay, next is, let's apply the equations of equilibrium here. So we have P sub 2, negative P sub 2 minus 45 plus 30. Negative P sub 2 minus 45 plus 30 is equal to 0. So P sub 2 is equal to negative 12. Okay, so negative 12. So this means that P sub 2 is equal to 12 kips compressions. Okay, so in other words, this one should be going the opposite direction. Okay, and then lastly is P sub 3, which is just simply 30 kips. Okay, so now we have this. We have the forces, and our working equation is the force deformation relationship that or let's write it here. Using force for compound section. Okay, so this is our working equation. So P sub I times L, the individual force, the summation of the individual forces, over AI times EI. Okay, so this is the ratio, it's not right here. Okay, so since we have a constant E value, so we can just take that out. We can take this out from this summation term. Okay, so let's just write 1 over E. So this is summation of I'll just run it right here. Summation of, I think, PI LI over AI. Okay, so let's continue. Okay, so 1 over E. So the first part is P1. Okay, so this section A to B. Okay, so the P1 right here is, or let's just write here, P1 L1 over A1, okay, plus P2 L2 over A2, okay, plus okay, plus what else? Plus P3 L3 or over A3. And by the way, this is an algebraic sum, so that means that if this is compression, then we have to take the negative value. Okay, so 1 over E, then our P1 is 60. Right, 60 times 10 to the 3, 8 times 12, the length is 12, all over area of 0.9 inches squared. Okay, plus, actually this is minus because this is compression, minus 15 no, not 15, this is minus 12, right? Minus 12 times the length of okay, times 10 to the 3 times the length of 12, right, all over the area 0.9. Okay, because it's the same area, it's the same sections. Okay, plus what else? The P sub 3. So P sub 3 right here. So this is 30 kips times 10 to the 3, okay, times 16. Okay, that's our length, and then the area is 0.3. Okay, so if we do the simplifications, then what we get right here is of course the value of E is this one, right? So what we get is a value of I think this is 75.9 times 10 to the 3 inches. Right, so that's going to be the total deflection of this problem. Okay, so this is now the equations we did the setup. Then if you do the mathematics, the computations, then you'll arrive in this value. Okay, so just to do a recap on what we did, we have a problem having a multiple cross sections, multiple lengths, plus multiple points of loadings. Okay, so if that's the case, our working equation would be the summation. So it's just simply the summation of, it's like this. It's basically the summation at 1 plus, the deflection at 1 plus the deflection at 2 plus the deflection at 3. Okay, so that's it. Okay, so first what we did is to set up the sections and then solve for the internal forces by applying the equilibrium equation. So once you have the internal forces, then you can actually solve for the, or you can apply the force deformation relationships to solve for the deflections. Okay, so once you have all that, then you can solve for the total deflections. All right, so I think we'll do another problem in the next video.